How's it going, everyone? Mr. Geyser here with lesson 13 on trigonometry and polar coordinates. In this lesson here, we have 5 main skills and learning objectives. First, we're going to plot points using polar coordinates. Second, we want to convert coordinates from polar to rectangular form and vice versa. Third, we want to transfer equations between polar and rectangular form. Fourth, we want to represent complex numbers in the complex plane. And fifth, and finally, we want to write complex numbers in trigonometric form. There we go. In this lesson, we will define polar coordinates and learn how they relate to rectangular equations. Students will convert from rectangular to polar and vice versa. So let's explore this and how we set up this system. In this here, we're given a polar coordinate system is a system to plot points in a plane with a point O in the center of a circular grid. Now, the pole is the point O, or the origin of this axis. Now, the axis is this polar axis here, where it's always positive and extends to the right-hand side horizontally from point O. Now, a polar coordinate, like point P here, is made up of a radius and some theta, or a direct angle. That radius is the direct line from point O to this point P, or really this point O to this point P, Q, R, S, all these other points. But this here is known as the radius from that center to our known point we're trying to go to, while the direct angle is the counterclockwise angle from this axis to that OP line. Let's explore this in example 1. We're going to plot these 4 different polar points. We're going to plot these points using these coordinate grids, and notice our process. First, we're given this 2 here, and we want to go 2 to the right because 2 is positive, making 2 our radius. Then, from this point here, we want to go counterclockwise pi over 4 to land at this position. That position there is exactly now where our point P is. Try that a couple more times. That's all we're doing with polar coordinates on this side. For this Q, we're given -1. Negative is going to go to the left-hand side. And then we're still going to go counterclockwise pi over 3. So from this point, we're going to go down that little slice to this point, where we can label it as point Q. Notice this negative aspect for the radius. When we're going negative, we go left from point O. When we go positive, we go right from point O. However, if we happen to have a negative theta, notice the different rotation we take. We still have a positive 3, so we go to the right 3 units. Then this negative pi over 6 is going to go down one little slice to this point, and then we just label that point R. Let's put both of those negatives together in our final part for part 1 with S. We're going to go -2 for our radius, which means we're just going to go left 2 units. Then we're going to go -7 pi over 6 around the circle here. So we want to go clockwise 7 pi over 6. We know a 180-degree rotation is a full pi. Since we have 7 pi over 6, we're almost going 7 slices around this pi here to land up at this position. And then we just label it as our point S. Let's explore this a little further in example 2. For example 2, we want to plot the point 2, 2 pi 3, and we need to find 3 additional coordinate representations of this point between that domain of -2 pi to 2 pi. What we want to explore is that all of these points on this polar grid can be represented in several different ways. That first point, for example 2 here, we're going to take that 2, go 2 over, and then we're going to take that radius, that theta of 2 pi over 3, landing our point here, and then we can label it as our point P. But we want to try and find a few other ways to find this point. Notice that we have 2 different equations or formulas we can use, where if we keep the radius the same, all we really want to do is take that theta and go a full 2 pi around the circle, either positive, or we can subtract 2 pi and land in that same position. The other way we can go about this is if we start with a negative radius, we're almost starting 180 degrees, or a full pi, behind or ahead of that first radius. Sorry, or that first theta, I apologize. Let's explore this about 3 times in part A. In part A, we can either add or subtract that 2 pi. So if we had this radius of 2, we could go a full 8 pi over 3 around this circle here. But again, that's outside of our domain given for this problem. Since 8 pi over 3 is a bit too big, because we added this 2 pi to our 2 pi over 3, let's just subtract it. When we subtract this, what's really happening is we're going a full 2 for our radius, and then we're going clockwise a negative 4 pi over 3 around to that same position. Let's explore 2 other ways to write this polar coordinate. So we're going to, over here, we're going to go negative 4 pi over 3 to land up there. The other 2 ways is if we start with that negative radius, we simply add a pi to it. When we have this here, we're going from negative 2 to 5 pi over 3. So we go back negative 2 here for our radius. We're still going to go counterclockwise around and land on that same position. This is basically 2 pi plus another pi to go the rest of the way to that polar point. That's where that plus pi comes from for that negative radius area. Now notice, for this third example, if we subtracted pi, but we kept r the same, all we have is we go back negative 2 here, and then we just go negative pi over 3 up to that point. For this example, we just want to showcase that we can rewrite our polar coordinates in several different ways and land up on the same position. Polar coordinates are very unique in that aspect. On a normal rectangular grid, every point in a coordinate grid, a rectangular grid, has a known x and y. For a polar coordinate, we have an infinite number of ways to write this point here by simply adding pi or subtracting pi when our radius is negative, or by adding 2 pi or subtracting 2 pi when we keep our radius the same as its original point. In this bottom right here, the relationship between polar coordinates and rectangular coordinates, to change from polar to rectangular coordinates, we can use these 2 formulas. For our x value really just is our radius times our cosine theta, and our y value is just our radius times our sine theta. In 2, we can then change from rectangular to polar coordinates using these formulas. If we're given x and y, all we need to do to find our radius here is just using good old Pythagorean theorem. We're going to use x squared plus y squared, and then we get r squared. And that's really just trying to find that radius by using that height and that horizontal displacement and that vertical displacement to find that diagonal. But for the second equation, notice that this provides us the angle. Tangent of theta is just equal to that ratio of y over x, where really we can manipulate this second equation to take the inverse tangent of y over x to find that theta. Let's try that out in a couple other examples. Oh, for this here, I apologize. For this here, let's just finish up example 2. For example 2, I had missed that, my apologies. In part B, we want to write the rest of these possibilities for these problems here. Notice that if we start at our positive here, we can start at either positive 2 or if we start at negative 2 for our possibilities. We can then add that first instance of this point. In the case of positive 2, we're going a full plus 2 here, and then we're rotating around counterclockwise to get 2 pi over 3. And for that negative radius, if we go back 2 units, we're going a full rotation of 5 pi over 3 to meet that same location. Now, for that first instance, when our radius is positive here, we simply want to add this 2 pi, a full period length, or we add 2 pi in the case of a radius being negative as well. And we still use our k values to indicate if we want to go positive 1 rotation around the circle or negative one rotation around the circle. Meaning that k here can be any integer, -1, 0, or even +1. Now, let's practice converting our polar coordinates to our rectangular coordinates. In example 3, we're going to find the rectangular coordinates of the points with the given polar coordinates. In part A, we're given p, 3, 5 pi over 6. So we're given these two equations to find our x and our y, and we're simply just plugging in our radius of 3 and our theta of 5 pi over 6 to find these values. For x, we just now have 3 cosine of 5 pi over 3. We then solve out cosine of 5 pi over 3 to get -√3 over 2 times 3. And then we just multiply that out to get x is -3√3 over 2. Try that one more time for y, where we're simply finding now that y is 3 sine of 5 pi over 3. And we know that 5 pi over 3 is just going to give us 1/2, and then 3 times 1/2 just gives us 3 over 2. These are our rectangular pair for our polar pair. Let's try that again in part B, where we're given q is 2, -7 pi over 6. And we can write this equation one more time for x and y, where x is simply going to be that 2 times cosine of -7 pi over 6, and y is going to be 2 sine -7 pi over 6. We solve out our cosine and our sine here to get -√3 over 2 and 1/2 here. That 2 times -√3 over 2 and that 2 times 1/2 just gives us that x as -√3 and that y as 1, making our q point equal -√3, 1. Now that we feel pretty good going from polar to rectangular, let's try it in reverse. In example 4, we want to find two polar coordinate pairs for the points with the given rectangular coordinates. In example 4a, we're given point P as 1, -1, where our x is 1 and our y is -1. So to find that radius, we're to use that Pythagorean theorem where we're solving for our r value. And we're given this known tangent theta is still equal to y over x. We're going to do a small manipulation to solve for theta here, where really it's just the inverse tangent of y over x. Let's go with the easy equation first to solve for r, where we're just plugging in 1 for x and -1 for y. That solves out to just equal √2. So we know our radius is going to be the square root of 2, while our theta is going to be, well, first let's plug in our y and our x. We end up getting -1 over 1, which that simplifies down to -1 here. And we know that the inverse tangent of -1 is going to be two different locations. That first location is at 3 pi over 4, and then that second location is a full pi away at 7 pi over 4. We need to determine which one of these thetas here is more valid. Notice that our coordinate point is at +x and -y, meaning that this is in quadrant 4. So we want to use the theta that's located in quadrant 4. Since we now know it's going to be in this point here, we can say that our polar coordinate is √2, 7 pi over 4. And since we know that polar coordinates repeat, we could also say that it's √2 a full 2 pi around at 15 pi over 4. And if we even wanted to, we can write a third one where it's -√2, something else. I'm curious to see if you guys can find the theta when our radius for part A is negative. Without further ado though, let's start with part B, where we're still given q, which is 2, 0 now. We're still given all those three exact same equations to find our radius and our theta. For our radius, we're just plugging in 2, where x is, and 0, where y is. And then we find that our radius here is just equal to 2. Since our y value doesn't exist, or it's 0, our radius just becomes that x coordinate. Really, it's just the length of 2. Same kind of thing happens for our tangent here, where we get 0 over 2, because our y is 0. So we're really trying to find the inverse tangent of 0, which occurs at those two locations of -1, 0, and 1, 0 on our unit circle. And since we're going to be located here, where our x is positive and our y is 0, we know that the real theta that we want to try and use is that 0 value for tangent, not pi, because that's what our two locations are. We now can say that theta is 0, and then we can rewrite this as 2 pi over comma 0, or we can add a full 2 pi here and say it's 2 comma 2 pi, and we can even say it's negative 2, and then we go a full pi length around. And notice this weird happenstance. If we go a full negative 2, we actually can go negative pi counterclockwise or clockwise to that same position here. It's kind of a unique point on our coordinate grid. Let's explore a few of these more in example 5, where when we want to plot a point in x comma y, noting the quadrant or the coordinate axis the point lies on. 2, it either is x equals 0 or y equals 0. We want to use a sketch to find our radius. Otherwise, we can use this radius equals the root of x squared plus y squared equation. 3, to find theta, where that point lies in, we can use one of these two equations. If we know it's going to be on the right side of our coordinate grid, we know we're going to use the inverse tangent of y over x, the normal kind of equation that we were just solving with. And we discovered that if we're in quadrant 2 or 3, where x is negative on the left side of our coordinate grid, we're just going to add the inverse tangent of y over x plus pi. Let's explore this again in example 5, where in example 5, we want to express the given equation in polar form. In part A, we're given y is equal to 1/2 x squared. Our first sign is we want to try and solve out for y and x to get into this polar coordinate. And notice, we want to try and use this here to replace our x and this to replace our y. We're now in polar form. We want to try and reduce it down just a little bit so it's in a simpler way. When we're simplifying this out, let's square out that cosine first. To square out that radius cosine theta, we now just have radius squared, cosine squared of theta. We're going to manipulate out that radius from both sides. There's no need to have that square there. And we end up with sine of theta, or 2 sine of theta, because we need to multiply out that 2, equals our radius of cosine squared of theta. So let's just get rid of that cosine from both sides, and now we have our radius by itself. So to solve this equation, we now have our radius is equal to 2 times sine of theta all over cosine squared of theta. Simplify that out just a little bit more. We're going to separate it here, and we can rewrite this sine and cosine and this 1 over cosine here as tangent of theta and secant of theta. So this equation here is exactly equivalent to the rectangular equation of y equals 1/2 x squared. Let's try that again with part B, where we're given 4 times x squared times y is equal to 1. So we first want to start with these y and x here, where we want to replace our x and our y with our polar equivalencies. We replace x with that radius cosine theta, replace our y with our radius sine of theta, and then we simplify out the equation to its simplest form. We're going to square out that radius there, or this radius and that cosine theta here. We then want to showcase that it's just r times r to the third here, and notice that we can actually separate this out just a little bit, where sine of 2 theta is equivalent to 2 sine of theta times cosine of theta. Now this 2 sine of theta and cosine of theta is within this 4 radius to the third, cosine squared, and sine squared. We can take out a cosine and sine in that 2, and we get this sine 2 theta as its equivalent. We're trying to reduce it down a little more. Our next step is just to divide out that 2 here, and that cosine, and that sine 2 theta all together to get our radius to the third is equal to 1 over 2 cosine sine of 2 theta. And unfortunately, the simplest form for part B is just saying the triple root of, or we can take this as a secant and cosecant here, but we're still taking this as a triple root of this overall equation here. Sometimes we just get a bit of an ugly polar form based off of our rectangular form here. Now, in example 6, we're going to convert each equation to rectangular form and identify the graph. We're going to support our answer using a graphing utility in polar graphing. What we want to showcase is that in part A, we're given the radius as 4 here. And we're still going to use this Pythagorean theorem where our x squared plus our y squared is going to be equal to r squared. We plug in 4 for r here, and then we end up getting 4 times 4 to get 16. This here was a pretty easy solve, but what I want to showcase is that for this rectangular equation, we can actually graph it using our TI-84s. Let's pop that up real quick. For our TI-84s here, what we want to showcase is to change our TI-84s into polar coordinates, all we need to do is change the mode. When we change the mode here, we're selecting mode, we're going down to where it says function, and then eventually you'll see polar somewhere on the right-hand side. You tab over until it says polar here, and then hit enter. Notice something immediately changes on our TI-84s, but if we select y equals, we now have all these radius inputs, and we know our radius is 4. Type in 4 for our radius here, and then when we go to our graph, instead of getting a line at r equals 4, we get a circle on our grid here. I know it looks like an oval here, but since our window is a little bit skewed on our TI-84s, it looks like an oval. We know that it's a circle because on the x-axis and the y-axis, it's a full 4 points from that origin. So if we go back to our slides here, this graph looks like a circle in rectangular form where r is equal to 4. Let's try that one more time here with part B, where part B, we want to try and convert it from this tangent of theta, which is just equal to our y over x here. We can write this in that as tangent of 2 pi over 3 is that terminal ray from our unit circle that goes in that quadrant 2 there. And we can find the x and y at that location. Well, at that location, our y is going to be root 3 over 2, and our x is going to be negative 1/2. We then can write out that this tangent at 2 pi over 3 is the slope of that terminal ray of negative root 3. If you already know your tangents across your unit circle here, this here is already a known fact for you. If you need to solve it out, all we're really doing is taking that y and dividing it by that x. Since we're dividing a fraction, we're going to keep, change, flip that operation to get that tangent there. Notice that when we graph this here in polar form, we actually get this equation where it's going to be negative 3x equals y, and we know these types of equations as a linear line where x has a slope of some kind. Well, if we bring up our graph here, we get this linear line that happens to be a negative root 3 as its slope. To make a little bit of sense of this line here, if we plot a unit circle on this grid here, we notice that this unit circle and then this blue line is just being derived from this terminal ray from our unit circle. Whenever we're given a theta, we know that our line should be some slope on our coordinate grid, but whenever we're given a radius, it's going to be some circle on our coordinate grid. The graph here is the terminal ray at that theta of 2 pi over 3. Let's try this 2 more times with part C and part D, where instead of finding these equations and then plotting them, we're going to go in a bit of a reverse for this lesson. We can actually say that the radius of 2 secant theta is going to give us this graph here. Notice that we were expecting to have a circle for that radius graph, but we end up getting like a straight line instead. So let's solve this out just a little bit to try and see how this occurred. For our radius here is just really equal to 2 cosecant of theta, where cosecant is just this 1 over sine of theta. Well, since we have that, We can now manipulate a little bit where it's just 2 over sine of theta. Well, let's just multiply both sides by sine of theta. And notice that this radius times sine of theta is how we write out y. Well, if y is now equal to 2, because our radius of sine theta was equal to 2, we know those graphs to be just a horizontal line across our axis. So for this graph here, the graph forms a horizontal line. In part D, we're given this radius is equal to 6 times cosine theta. So let's explore this a little bit, where if we rewrite it, we actually get this weird oval shape to the right-hand side of our axis. So let's rewrite this equation as radius is equal to 6 times cosine of theta, where if we multiply radius on both sides, we're just bringing radius out of nowhere, but trust me here, we get our radius squared is equal to 6 times radius cosine theta. The reason why we had to multiply radius to both sides, right, we're bringing this out of nowhere, is because we want this here to equal our x. Now that we have radius squared is equal to 6 times x, we can convert this by saying our radius is just equal to our x squared plus our y squared. Notice we now have no radius, we have no theta, we just have this equation in terms of x's and y's. And now if we subtract 6x to both sides, we have all of this on the left-hand side and 0 on the right-hand side. Notice that we want to use one of those perfect square theorems to try and solve this out here. If I'm given x squared minus 6x, for these two terms here, I know if I were to add 9 to this term here, and I have to add 9 to the other side, I can actually simplify that out just a little bit by saying it's just x minus 3 squared. I still have my y value squared over here, but remember that this equation here of x squared plus y squared is equal to our radius squared. For this, notice how our radius for our circle here is actually equal to 3. We'll showcase this in just a second, where our point here, our center point is at 0, 3 with a radius of 3, where the graph forms a circle with a radius of 3 at the center of 0, 3. Notice the pattern where that 0, 3 is coming from. Notice that our 3 in this point here is coming from the fact that we have a minus 3 for our h attached to our x. Notice that that 0 here in that 0, 3 pair is coming from the fact that our y here has a 0 attached to it. And I've just noticed here, let me rewrite that point there. It's not 0, 3. It's going to be 3 for our x, 0. That was my bad. Our 3 here in our x is coming from this h here from our x. The 0 here for our y is coming from the k here from our y. Remember those hk forms from a long time ago? If you don't, no worries. We're going to explore it one more time in example 7. In this final example here, we're going to convert x minus 3 squared plus y minus 2 squared equals 13 into polar form. My first step here is just to rewrite that equation. And now I want to try and solve it out just a little bit, so I'm simplifying it. I'm going to square out that x minus 3, this y minus 2 to get this form. I'm then going to try and add those constants, subtract those constants from both sides. Eventually, I happen to get 0 on that right-hand side. I then can rearrange this just a little bit so that I have my x squared plus my y squared over here, minus my 6x, minus my 4y is equal to 0. From this point, I can actually rewrite all of my x terms as radius cosine theta, and my y terms as radius sine of theta. And since we rewrote that x squared plus y squared using that associative property, it groups them together, we now have our radius squared over here. We now can subtract those terms, or we can pull out a radius from both sides here. A small example is that our radius here cannot equal 0. If it equals 0, then we have a point, or we have a circle that has a radius of 0, so it's just a point here. So we actually simplify out that radius over to here. And now we have our radius minus our 6 times cosine theta minus our 4 sine of theta. Well, let's just subtract those two terms to both sides, and now we solve for our radius. Now, if we were to plot this on our TI-84 calculators in polar form, we end up getting this equation here. Now, instead of trying to solve out all of this equations to get the polar form from that rectangular form, let's just go directly from this rectangular form to this graph here. Notice where the center point of this circle is coming from. The center point is coming from this -3 and this -2, where really it's going to be +3 for h and +2 for k. We know that this is going to be the center of our circle here, with our radius still being this root of 13. Because we know that this is going to be equal to our radius squared, so our radius is just going to be the square root of 13. Thank you very much for joining me on this first lesson for plotting out these polar coordinates. If you have any questions at all, please leave them in the comments down below, and I look forward to seeing all of you guys in class. Take care.